All right, everybody. Tonight we're going to be talking about performance. So this is week 8 of the ground, and we're going to start with something we've gone over already, which is pressure altitude. So pressure altitude is your height above the standard datum plane. The SDP, or the standard datum plane, is a theoretical level at which the pressure of the atmosphere is 29 or 9 or 2. So as we know, setting the altimeter to 29 or 9 or 2 will give us the pressure altitude. You can also calculate the pressure altitude with the formula that I taught you in class. Remember, so you need the field elevation and you need the current altimeter setting. You go 29 or 9 or 2 minus the current altimeter setting, multiply that number by 1,000, and then you add that or combine it actually with your field elevation. Okay, so a lot of times if it's a negative number when you combine, you'll actually be doing subtraction. The important thing to remember about the pressure altitude is that it's the height above the standard datum plane. So what I mean by that is the FAA on the written likes to ask that question, and the answer will be the height above the standard datum plane. Okay, it's just the theoretical altitude at which 2 9 or 9 or 2 exists, given the current atmospheric conditions. Then we have the density altitude. For the density altitude is the pressure altitude corrected for non-standard temperature. So this is the altitude that the aircraft feels like it is flying at. So when we have a low density altitude, that's a good thing. When you have a high density altitude, that's a bad thing. Okay. So a low density altitude, let's say you calculate your density altitude and it's 300 feet. Okay. And we're out at Delaware, which is their field elevation is 1,000, right? So if our density altitude is 300 feet, that means that the air is denser, right? A lower density altitude actually means higher density air. Higher density air is better for the aircraft. It's the engine will combust more efficiently, and there's more molecules for the wings. There's more air for the wings to use to fly, right? A high density altitude, so let's say it's 5,000 foot density altitude, is a bad thing, right? If we're taking off and the aircraft already is going to fly like it's at 5,000 feet when we're on the ground, that's not a good thing. The aircraft is not going to perform as well as we would like it to. So remember, the density altitude is the pressure altitude corrected for non-standard temperature. So the biggest thing that is going to affect the density altitude is temperature, right? Higher temperatures, which we'll talk about here in a second, are going to give us higher density altitudes. Lower temperatures are going to give us lower density altitudes. So we need to talk about the factors affecting performance, okay? So first thing that we'll talk about is pressure. So when we have a higher pressure, that equals more air molecules in a given volume, right? That's higher density. So when we have high pressure, that means we have higher density of air. This is going to increase the lift and the combustion power of the engine. That increases our performance. Okay, when we have lower pressure, that's less air molecules in a given volume. It's going to give us lower density. This decreases lift and decreases combustion power of the engine. Okay, so lower pressure is going to give us worse performance. Higher pressure gives us better performance. So let's say you go out there one day and the altimeter setting is 3030. Well, that's high relative pressure compared to 29 or 9 or 2. So that's going to be a uh, situation where the density of the air is higher, and it's going to make our density altitude lower. Okay. If you go out there and it's 29 or 35, that means it's lower pressure, so the air is less dense. So our density altitude is going to be higher. Okay. Temperature. Higher temperature causes the air to expand, which lowers the density of the air. When you have lower density, that's going to be lower performance. Lower temperature causes the air to condense, increasing the density of the air. Higher density, higher performance. Okay, so if you can think back to how pressure and temperature relate to the density of the air, you can figure out what the effect is going to be on performance, right? If it's going to be higher density air, it's going to be better performance. If it's lower density air, it's going to be worse performance. Humidity is our third factor that affects performance. And the way that humidity affects it is the more humid an air mass is, the more water it will hold. Because water vapor is less dense than air, this slide is worded poorly, but Because water vapor is less dense than air, high humidity air is less dense than dry air. So high humidity decreases performance. We don't really have anything that measures this factor because it's not nearly as big of a of an impact on performance compared to temperature and pressure. But just know that it's another thing that is going to make your performance worse if the air is very humid. Elevation is going to impact our performance. This one's really, really simple. So the higher the airport elevation you have, it's going to result in higher density altitudes. High density altitudes are equal to worse performance, right? So always be aware of your elevation and thus your density altitude. So if you're uh, out west, you're in Colorado and you're at a field that's 5,000 feet above mean sea level, you're already starting out at a high elevation, which is automatically going to make your performance worse, right? You need to calculate your density altitude, and your density altitude automatically is already going to be elevated because you're at higher field elevation. Runway surface. So the runway surface is going to impact our performance. Any surface other than paved is going to result in worse performance. It's going to give us longer takeoff rolls, longer landing rolls, because let's say you're taking off on grass, right? The airplane will have a tendency to sink into the ground because it's soft. Well, you're going to have to use more energy to overcome that sinking to start your takeoff roll. Uh, so you're going to have a longer takeoff roll. When you're landing, grass generally will have less friction than a asphalt runway. So when you're landing, the airplane doesn't have as much traction when you're landing and starting to brake. So you're going to have a longer landing roll. You also need to think about sloped runways. So there are, some runways are sloped. You can find in the AFD the slope of the runway. Usually it's minimal, but there's places that have a considerable slope. Okay, when you have a sloped runway, let's say you're taking off down a runway that is sloped downwards, so you're taking off downhill. That is actually going to decrease your takeoff roll, so that's a good thing for you. But if you're landing on a sloped runway that is sloped downward, that's going to increase your landing roll. Okay. The opposite is true for an uphill runway. So if you're landing uphill, your takeoff roll, I'm sorry. So if you're landing uphill, your landing roll will be shorter. If you're taking off uphill, your takeoff roll will be longer. A wet runway is going to increase your takeoff and increase your landing. The reason for it increasing your takeoff is now you have water on the runway. You have to fight through that water, slug through that water to take off, right? Imagine trying to run in 1 foot of water. It's not easy. For landing, it decreases the airplane's braking effectiveness. Okay. Wind. So headwinds increase performance, tailwinds decrease performance. This is in relation to takeoff and landing, right? So at takeoff, a headwind is going to decrease your takeoff roll, and a headwind is going to decrease your landing roll. A tailwind is going to increase your takeoff roll, and a tailwind is going to increase your landing roll. Always avoid taking off and landing with a tailwind if possible. Okay. Um, if you ever look in the performance charts for most airplane, it'll tell you that for every 2 knots of tailwind, you increase your landing roll 10% or your takeoff roll 10%. So think about that. 2 knots is not a lot compared to an increase of 10% in your landing roll. That's a lot. So always, always, always try to land with a headwind when you can and avoid a tailwind. Right here we have the density altitude chart. So we've gone over this a couple times. Um, Remember, always pay attention to your axes here. So this is your density altitude, this is your air temp, and these are your pressure altitudes right here. So in this scenario, we would have our temperature and we'd also have our pressure altitude. So we'd go over to our temperature, then we'd go up to the slanted line that represents our pressure altitude. Let's say it's 3,000 today. You go straight over and you'll get your density altitude. This is a crosswind component chart. So the way that the crosswind component chart works is um, you'll be given a wind direction and a runway. So let's say the wind is 100 and the runway is 18. Okay. Well, 100 is 80 degrees off of runway 18. And then they'll give you a wind velocity. Let's say the wind velocity is 30 knots. Okay. So you'll find the 30 knot wind ring you'll go to the 80 degrees and you'll follow that to the 30 knot wind ring. Okay, so it's right here. Once you get to that point, you'll go straight down and you'll find the crosswind component. So it's about 29 knots. And you'll go straight over and you'll find the headwind component, which is about 5 knots. Okay, so that's how you use one of these. Cruise power. So we did talk about this when we talked about planning flights, but this is very normal for you to see in terms of a chart just in a POH for anything. You know, takeoff landing charts can look like this. Cruise power setting charts usually look like this. So what you'll do in this case, it's showing us a 65% max continuous power cruise power setting at 2,800 pounds. So what you would do is you'd find your pressure altitude or the altitude that you want to cruise at or whatever's closest to it. Remember, always go for a worst case scenario. So if we're cruising at 5,000, we're going to use the 6,000. If we're cruising at 7,000, we're going to use the 8,000. Okay, don't use 4,000 if you're cruising at 5,000. Okay, always go worst case scenario. And then you'll choose the temperature that is closest to what you see representing what that day's conditions are after you check the winds and temps. Okay. And then it's as simple as that. You'll go in here. Let's say it's a standard day. We're going to cruise at 6,000, or let's say it's plus 20 degrees at 6,000. We'll go here. What we'll see is the RPM should be at 2450. Our manifold pressure would be 21 inches. Our fuel flow should be 6.6 psi and 11.5 gallons per hour. And we should get about 161 knots true airspeed or 185 miles per hour. We'll look down here. We'll see full throttle manifold pressure settings are approximate, and the shaded area represents operations with full throttle. So what they're saying down here in the shaded operation is you're going to be at full throttle, okay, in these situations. This is a spaghetti chart right here. So you can see these sometimes. Piper likes to use spaghetti charts. I think the Diamond has spaghetti charts in them too. So this is just a way to calculate your takeoff and landing distance. So let's do this example problem right here. So you'll start with your outside air temperature. We would have already calculated our pressure altitude. In this case, it looks like it's 19 degrees out. So we'll go 19, and it looks like we have 2,000 foot pressure altitude. So you'll start at 19, you'll go straight up till you hit your line of 2,000. Then you go straight over. Okay. Next, so our point is right here. Next, it looks like our weight in this case is 2,600 pounds. So what you're going to do is follow the slope of this trend line here, but from your point down to the 2,600 line. So we're right here. We're going to just mirror this slope down to the 2,600 line. Stop right here when we get to our weight. You go straight across. Now we need to factor in our wind component. So it will show us our headwind all the way to 30 knots. In this case, it looks like we have about a 5 knot headwind. So we'll follow this line down to 5 knots and you'll go straight across. Okay. Right here, we have our obstacle height. So they give you an obstacle height from 0 to 50. So if we had to clear a 50-foot obstacle at the end of the runway, we would follow the slope of this line up all the way over to 50. Or if we're not clearing anything, we'll go straight over. And then you have your takeoff distance. In this case, it looks like about 900 feet. This looks like about 1,500 feet, close to 1,500. So that's how you do these. What's this one? This looks like it's just landing. This is a landing. It's the same thing. It works the same way. You can notice here, though, that it's giving you the associated conditions. So this is what they are assuming you are going to do. Okay, if you don't follow these associated conditions, this will not be accurate. Okay, your calculation will not be accurate if you're not landing with, or if you're not taking off uh, the way that they prescribe. Same goes for landing. There's another chart you can see. You'll see this in the 172s. They make it real straightforward for you. Okay. They give you your conditions, flaps 40, power off, hard surface, zero wind. Okay. You'll find whatever weight closely matches yours, and you'll find your altitude and temperature that matches yours the best. So Usually you're not going to be sea level in 59. A lot of times you'll be a little closer to this, so you'll end up using this number. You can see the notes down here. Always, always, always remember to read the notes. Decrease the distances shown by 10% for each 4 knots of headwind. So what they can do on the test is they'll ask you what the landing distance will be at 2500 and 50 degrees Fahrenheit, but they'll also include in the conditions that you have a 20 knot headwind. So 20 knots headwind, you need to decrease 10% for each 4 knots. 20 knots is 20 divided by 4 is 5, so it's a 50% decrease. So the answer would actually be, 235 feet. Okay. You can see here increased distance for 10% by each 60-degree Fahrenheit temperature increase above standard, and for operation on a dry grass runway, increased distances by 20%. Okay, VORs. So VORs are hard to teach over the computer. So I'm going to have you watch a video. I'm going to send you a link to a video that's going to teach you how to read these, and then we'll work on it together in person. But what VORs are, they're at this point, outdated form of navigation. They're a system that traverses all of North America and all of the world, really. They're slowly being decommissioned as we move to GPS, but they are retaining a minimum number of them in case GPS has a failure, right? So we can use these to get around. This is a picture of a VOR. So if you ever see something like this in the middle of a field, that's what it is. How do they work? So VOR frequencies are between 108 and 11795. You don't need to know this for the written. You don't need to know this for your test. It's just good information to know. The station emits one stationary master signal and one rotating variable signal. The signals are also called reference and variable phases. And the aircraft equipment measures the angle between the two signals and determines your position relative to the VOR. They operate, this is important, this is what you need to know. They operate on line of sight, meaning if a physical object is between you and the station, you will not receive an accurate signal. So if there's a mountain between you and the VOR, not going to work. There's a bunch of buildings between you and the VOR, not going to work. There are three types of a VOR, three classes. You have a high altitude, terminal, and low altitude, and these are their distances and their usage distance. So the high altitude from 1,000 to 14,500, you can use 40 nautical miles an in. From 14,500 to 18,000, you can use it from 100 nautical miles an in. From 18,000 to 45,000, you can use it 130 nautical miles in. Then from 45 to 60, it goes back to 100. Terminal is just 1 to 12 at 25 miles, and low altitude is 1 to 18 at 40 nautical miles. This is what they look like on a chart. So there's three different types. You have a VOR, which is just a standard VOR, a VOR DME. So DME is distance measuring equipment. What that means is you will also be able to get a reading of how far you are from the VOR, from a VOR DME. A plain VOR will not give you a distance. A VOR DME will. And then a VORTAC is a military VOR. So this is what a VOR indicator looks like. What you have here is your course needle, called your CDI, in the middle. You have the to from flag, and then you have the OBS, okay, the Omni Bearing Selector. So how this works for you, what you will see is you'll spin this OBS knob, and this CDI in the middle will swing to the left and the right. Um, One radial here, actually two radials, will cause the CDI needle to center, and that is going to give you a bearing. Okay, it is going to give you your bearing to or from the station, which we'll talk about more in class, but if you watch the video, it'll explain that to you. So this flag will show to or it will show from, which will be an arrow pointing the other way. If you have this nav unreliable signal, that's going to mean that the equipment is detecting that the indications that it's receiving are not reliable. There's three types of VOR checks that you can do, that you must do within 30 days if you're going to use the VOR equipment as your primary means of navigation. You have a VOR test facility, you have airborne checkpoints, and you have ground checkpoints located on airport surfaces. So they must be checked within 30 days. The ground test tolerances are plus or minus 4 degrees. The airborne tests are plus or minus 6 degrees. Okay, a VOT. So a VOT is a test that you will find the frequency for in the airport flight directory. So this is a test that it exists at certain airports. You'll go into the AFD and it'll give you a frequency. Let's say it's 1085. So I tune in 1085 to my nav radio. And then in the AFD, it'll also tell you, well, actually, it just tells you the station. And you'll set the course selector to 0, and it should line up. Okay? You set it to 0 and it should be centered and it should say from. Then you should set the course to 180 and it should say to. Okay? The maximum error allowed on this is plus or minus 4 degrees. So 180 and it should say to, or 0 and it should say from. If you do a certified airborne checkpoint, it's plus or minus 6. You will find that in the AFD also. It'll describe where you need to go and what VOR to tune to, and also what radio to tune to. And then certified ground checkpoints, once again, you'll find in the AFD, and what you'll do is you'll tune a certain VOR, you'll tune the radio they tell you, and then it'll tell you where to go on the airport. Okay, and it has to be plus or minus 4 in that situation. The cone of confusion. So this is a error that VORs have. What happens is as you approach the VOR, the radials become closer. So it's easier to draw this out. Let's see. Here, this works. So you can imagine a VOR looks like this. As you get closer to the VOR, all these radials come closer and closer together. So once you get very close to the to where the VOR physically is in space, you enter what's called the cone of confusion. The equipment can no longer tell where you are at. What you will see is your CDI, that needle that we looked at, will swing out all the way. Okay. What you should do in this situation is just continue on the heading that you were on, or turn to the heading that you know you need to be on for your next navigation point, and wait for the to get further away from the VOR. Okay. You'll know that you've crossed over the VOR and passed it when it flips from to from, when the indicator flips from to from. Okay, so this is what it would look like. Flying, the radials are getting closer and closer. You're very close to the VOR. It can't tell where you're at. Then you cross away from it, and it starts giving you the from indication. Okay, reverse sensing. This will be easier to observe in the video, but it occurs when you're flying to the station with a from indication or flying from the station with a to indication. So when you are flying to the station, but you have the equipment set up to indicate from, the equipment is going to behave in the opposite way that it is supposed to. Likewise, if you're flying from the station or away from it, and you have the equipment set up to give you a to indication, it will operate in the opposite manner in which you want to. And here's the YouTube video that we're going to watch. All right, that's it.